Today we're going to talk about another subspace of N space, or another subspace of Rn. We're going to talk about the solution space to the vector equation Ax is equal to 0, where A is a coefficient matrix and X is a variable matrix. This solution space is called the Null Space. The dimension of the null space is called the nullity of A. And we're going to observe that the rank of A plus the nullity of A is going to be N. We're also going to look at systems of equations. We're going to look at consistent systems that are dependent. And we're going to notice that solutions follow a particular pattern. For those of you who have already had differential equations, you're going to see something that you observed in solving higher order DEs, non-homogeneous higher order differential equations. For those of you that have not had differential equations, you're going to see what you have to look forward to. So let A be an M by N matrix. The set of all solutions of Ax equals 0 is a subspace of Rn. So the set of all solutions of Ax equals 0 is the subspace of Rn. Now X is your variable matrix, so that would be of the form column matrix X, Y, Z, so forth, for 3 space. Proof. Your vector matrix, or your variable matrix, has dimension of n by 1, where it's n rows by 1 column. Like I pointed out, it would be the column matrix X, Y, Z for 3 space. Therefore, the set of all solutions is a subset of R sub n, because we just have n by 1. So we might have something like 1, 2, 3 would be a solution for in 3 space, which would be a subset of R cubed. The solution set is not empty, since 0 is a solution. So going back, obviously 0 would be a solution, because matrix A times the 0 column matrix is going to give 0, because you'll be multiplying by zeros in all cases. It's a big 0 matrix. So clearly, it is not empty. So to show that something is a subspace, I have to show 3 things. That it's not empty, that it's closed under addition, and that it's closed under scalar multiplication. So clearly it's not empty, since we have 0 as the solution. So now we must show that subsolutions is closed with respect to vector addition and scalar multiplication. Again, to show that something is a subspace, you have to show 3 things. It's not empty, that it's closed with respect to vector addition, and it's closed with respect to scalar multiplication. Well, let's look at vector addition first. Let's let x1 and x2 be solutions. Then if the solution space is closed, then x1 plus x2 must be a solution. So if x1 and x2 are solutions, then if we have closure, x1 plus x2 must be a solution. Well, if x1 and x2 are solutions, then ax1 is equal to 0 and ax2 is equal to 0, because we're looking for the set of all solutions to Ax equals 0. So if these are solutions, they make the equation true. Then I know that Ax1 plus Ax2 would equal to 0 plus 0, which is just 0. by using the distributive property, I can factor out the a to have a times x1 plus x2 equals 0. Well, this means that a times this vector equals 0, which means that this vector is in the solution set. So we've proved closure under vector addition. Now let's consider scalar multiplication. A times cx1. Now if a times cx1, we're seeing if I could multiply by the scalar, c times x1, I've got proof that c times x1 is a solution. Well, a times cx1 is c times ax1 by using the associative property. Well, ax1 is a solution. I mean, x1 is the solution, so therefore ax1 is 0. C times 0 is 0. So if a times a vector is 0, then that vector is in the solution set, so cx1 is the solution. So we've shown that vector addition is closed, scalar multiplication is closed, so we conclude that the set of all solutions is the subspace of Rn. We've satisfied all three conditions. Now this subspace is called the null space or solution space. I've already used the term solution space. It's called the null space or solution space of A and is denoted by NA. The dimension of NA is the nullity of A. So the dimensions of NA is the nullity of A. Find the basis and the dimensions of the null space for 4x minus y plus 2z is equal to 0, 2x plus 3y minus z is equal to 0, 3x plus y plus z is equal to 0. I can write it in the ax equals 0 form as 4, -1, 2, 2, 3, -1, 3, 1, 1, times x, y, z is equal to 0. I can row reduce this matrix using derive. So, in fact, what I did, I put the constants with it to row reduce the 4, -1, 2, 0, 2, 3, -1, 0, 3, 1, 1, 0, the way we solve systems, and I went to derive, I authored the matrix, had derived to row reduce the matrix, and we can read the solutions. Well, reading the solutions, I see that x is 0, y is 0, Z is 0. So we said find the basis and dimensions of null space 4. Well, the only element in the null space is the vector 0, 0, 0. The nullity of A, which is the dimension of the null space, is going to be 0. Because if the vector space consists only of the 0 vector, then we say its dimension is 0. Now let's notice something. Let's go back to the rank of the row space of A, or the rank of A, which would be the dimensions of the row space. The row space would have dimension 3, because I have 3 non-zero rows. So the rank of A is 3. The nullity of A is 0. 3 plus 0 is the dimension of my matrix. We started with the m by n matrix. Or in this case, 3 by 3. So n would be 3. Well, that's true in general. That is, that n is the rank of A plus the nullity of A. So the rank of A plus the nullity of A is equal to n. Or another way of saying it is that the number of columns of a matrix is equal to its rank plus its nullity. N is the number of columns because you had an m by n matrix. So let's look at a theorem now. If x sub p is a particular solution of ax equal b, so xp satisfies the equation ax is equal to b, then every solution of this system can be written in the form x is equal to xp plus xh, where x sub h is the solution to ax equal to 0. This should still be bold. Now the h comes from the homogeneous system. Ax equals 0 is a homogeneous system, so axh comes from the solution to the homogeneous solution. So every solution, the general solution, can be written in the form of the particular solution plus the solution to the homogeneous case. Now, as I said earlier, if you've had differential equations, pay close attention to the proof of this one, because in DE, I did not prove it for you. I just gave it to you and told you to use it. In this course, we prove it. Okay, proof. We'll let x be any solution of ax is equal to b. Now, ax equal to b and axp equal to b, because remember in the theorem we said that xp is a particular solution. So x is going to be any solution. xp is going to be a particular solution. So ax equal b and axp equal b implies that ax minus axp is equal to 0. Because that would be just ax minus axp be b minus b, which is 0. Implies that a times x minus xp is equal to 0, because I can use the distributive property in reverse, factor out the a. Well, if a times a vector is equal to 0, then that vector, x minus xp, is a solution to the homogeneous system. Now, the homogeneous system meaning a times the vector is equal to 0. Well, this implies that x minus xp is equal to xh, because xh was the set of all solutions, was one of the solutions to the homogeneous system. So xh stood for the solutions to the homogeneous system. X minus xp is the solution to the homogeneous system. xh was the solution, so therefore they're equal. Now the next step is just simple algebra, just add xp to both sides. So we get x is xp plus xh. That's a little clever proof that you may not have thought of on your own, but now that you see it, you should easily understand it and appreciate its power. Well, let's use this theorem to solve a system. Let's solve 2x minus 4y plus 5z is equal to 8, a negative 7x plus 14y plus 4z is equal to negative 28, 3x minus 6y plus z is equal to 12. Well, the first thing we want to do is to find a particular solution. So we'll try to find a particular solution. I can write the equation in matrix form as 2, negative 4, 5, 8, negative 7, 14, 4, negative 28, 3, negative 6, 1, 12. Now we could do it by hand and row reduce it, but since you should already be good at row reducing, we'll let you use derive. If you're not good at row reducing, you need to practice until you are, but then once you get good, use derive. So you'll notice I have authored the matrix 2, negative 4, 5, 8, negative 7, 14, 4, negative 28, 3, negative 6, 1, 12. Then I row reduce. So I just say row reduce number 4. So I have to do the go to author expression, row underline reduce, number 4, and this is what derive will print, and then I tell it to simplify. Well, once derive simplifies, I get this result. What do we see here? I know that x minus 2y is equal to 4. And here I get that z is 0. Well, I need a particular solution. So I just need to find something that makes it true. I know I have to use z as 0. Well, if I let x be, let y be 1, then I have x minus 2 is equal to 4. That means x would need to be 6. So I have, if x is 6, y is 1, and z is 0, I have a particular solution. 6 minus 2 is equal to 4. Z is 0. So we can see that one solution is going to be 6, 1, 0 when I write it as the column matrix. So I can come back and I can write that xp is equal to 6, 1, 0. Now we need to find xh. Well, xh is going to be the solution so that a xh is equal to 0. That's going to be a solution to the homogeneous system. Well, the matrix for that one is going to be 2, negative 4, 5, 0, negative 7, 14, 4, negative 28, 3, negative 6, 1, 12. I'm sorry, these are zeros. I was doing the same one again. These are zeros because I'm doing a homogeneous system now. So the constants were zeros. 2x minus 4y plus 5z is equal to 0. Negative 7x plus 14y plus 4z is equal to 0. 3x minus 6y plus z is equal to 0. So just replace the constants by 0. That's your homogeneous system. So I'll go back to derive, and I'll author my homogeneous system, and I row reduce it the same way, and this time I get x minus 2y is equal to 0, and I get z is equal to 0. Well, if x minus 2y is equal to 0, that means x is 2y. So if I let y be 1, x is 2, or how we want to do that, but what I'm going to do is to put in the parameters, and we'll let y be t and x be s. So I get s is 2t. Z would be 0, so I can see that x to the h is all the form 2t, t, 0. Or I can write this in the form of t times 2, 1, 0. So then my solution X is going to be XP plus XH, which is going to be 6, 1, 0 plus T times 2, 1, 0 for some real number T. Or I could write this as six plus 2t, 1 plus t, 0, if I wanted to add the matrices. But the top form would be the preferred way of writing it.